Welcome everyone! In this video I will give a short introduction into robotics, what a robot consists of and what we can expect from a robotic system. You've probably seen some robots before or read about them in the news. There are robots helping firemen to stay safe, there are robots helping out cleaning up oil spills, but there are also robots that you might not call a robot at first sight. For example, there's a robotic system generating power from kites. But also some exoskeletons can be considered robots. So what we can see from these examples is that the robots are mostly used for dirty, dull or dangerous tasks. But it can also help out making our lives and work a bit easier. You also saw that robotics is quite a broad field. This is probably also why there is not one agreed on definition of a robot. My definition of a robot would be a non-biological physical system that senses the world around it and acts on this world in order to accomplish a certain goal or task. If we leave out the non-biological part, this definition should also apply to humans and other animals. It also should be a physical system, so not a simulation. The system should also sense the world and change the world or itself. And lastly, it should try to accomplish a certain goal or task. This task might be as easy as following a light source, but could be as complex as driving around autonomously. Let's have a look at what we would need to build a robot. Usually when we describe a robot at its highest level, we are talking about a sense, think, act loop. This is the model describing the data flow between the robot and its environment. First, the robot will sense the environment. This also applies to us. We also sense the world around us by using our senses, ears, eyes, etc. Robots would use sensors for this, like cameras and microphones. The robot also needs to process this data to be able to decide what to do next. We use our brains, robots use computers. The level of thinking needed highly depends on the goal or task, of course. Simple tasks might even be solved without computers, but more complex tasks need more compute power. This is where embodied AI comes in, using AI to let a robot decide what to do. Lastly, the robot needs to act on this world in order to change itself, the environment, or both. And from that, the loop continues, and we'll start again by sensing the changed environment. We can map this model to the hardware needed to build a robot. Sensors, of course, map to sense, compute powers map to think, and actuators map to act. But we also see some extra hardware. Of course, the environment, the world around us, is analog, while the robot and computer are digital. So this signal, the physical property the sensor is measuring, should be converted into a digital signal. This is done by the analog to digital converter, or ADC. Similarly, we also need to convert this digital signal back into the analog world using a digital to analog converter, or DAC. But sometimes this is not enough. Usually the compute power only allows a maximum current through its system, while the motors require more current. This can be solved by adding a motor controller, also called H-bridge. An H-bridge is basically 4 switches making sure the motor can only get the current it needs, but also allows the motor to turn into 2 directions. We already saw that robotics is quite broad, and this is also reflected in the fields needed to build robots. Of course, this includes computer scientists to program the robot, but also electrical engineers to make sensors, actuators, and the converters. But we also need mechanical engineers, interaction designers, psychologists, biologists, just to name a few. Robotics is a combination of science and engineering. By engineering the robot, we might learn more about nature, and scientific breakthroughs can influence the way we engineer the robot. With this hardware setup, we can of course build a lot of types of robots. We can build drones, cars, boats, but also robotic arms with this hardware set. They mostly differ by way of moving something or themselves from point A to point B. Let's have a look at what this means. The easiest way to move something from A to B would be a conveyor belt. In this case, B is static, can only move from A to B. If we look at manipulators or robotic arms, they have a bit more freedom. The robot itself is still static, but the reach is limited to the arm. If you go one step further, we move on to mobile robots. They are dynamic, so they can move around. They usually use wheels and are therefore still limited to mostly flat surfaces. Robotic boats have the same limitation, since they also move in a two-dimensional plane. To overcome the flat surface problem, humanoid or legged robots can be used. They are not limited by a flat surface, but can also walk stairs. Therefore, they are a lot more agile. The downside is that walking is still quite complex to engineer. And lastly, you of course have drones. They are not even limited to surfaces, but can fly freely. This of course also holds for submarines. The downside is they have a limited payload and battery lifespan. You can imagine that all this complexity can be really hard to engineer. But apart from the complexity, why is building robots so hard? Of course, there's the problem that you need different disciplines working together, but mostly it is because we do not have the best techniques yet to do all these complex things that we as humans can do. Humans are really good at handling uncertainty, which is really hard for robots. Robots, on the other hand, are really good at precise repetition, which is really hard for humans. Overall, you could say that tasks that are easy for humans are hard for robots, and vice versa. This is why we need to work together. Since there is not one robot for all tasks, there is no artificial general intelligence yet. We need a different robot for each task. Therefore, it's really hard to find a good business model for your robotic application. This might be why at your home we only have a robotic vacuum cleaner or lawnmower. But will this change? Getting to more complex tasks often also means more complex environments. To get there, we will need better sensors, algorithms, and actuators. Technological breakthroughs in sensor technology, for example the precision of the sensor, but also the ability to measure new things, can help. The ability to process this data even better and make better decisions will also help. And lastly, better actuators, for example soft grippers, can also contribute to robots being able to perform more complex tasks. By doing so, we already have robots that do not need a cage around it anymore, but where we can work together with the robot. Step by step, we will see robots being able to perform more and more complex tasks in more and more complex environments. With this presentation, I hope you got a bit of an understanding what robotics is and why engineering robots might be harder than you think.